Well, welcome everyone to this April edition of the seminar series for Technologies for a Resilient Power Grid, put on by the TCIP project. We're really pleased to have you all here, and we're really thrilled to have a good friend of TCIPG, Dr. Ed Schweitzer from SEL. And I'll tell you a little more about that in a minute, but I want to make a few announcements. I'd like to remind you all that registration is open for our TCIPG Summer School. You can find information about that on the web, and that will be from June 15 to June 19. Scholarships are available to graduate students from U.S. institutions. These are generous scholarships provided by our sponsors, Department of Energy and Department of Homeland Security. So we encourage you to apply for those. They provide a substantial portion of the support for graduate students to attend the summer school. And the due date for those scholarship applications is April 15th. Early registration rate for the summer school ends next Friday, April 10. So please check that out. We've had a really strong turnout so far, and we hope you can all join us on the summer school. So now I'll turn to today's seminar. As I said, it's my really distinct pleasure to introduce Dr. Ed Schweitzer. Schweitzer is the lead of Schweitzer Engineering Laboratories, and he's been with us, and his people have been with us since the very beginning. I think back in 2003, when we got serious about working on cybersecurity for energy delivery systems, SEL was here. SEL helped guide us. SEL has been our supporter throughout all those years. Ed is world-renowned in his own right in this field. He received his bachelor's and master's degrees in engineering from Purdue University. He received his doctorate from Washington State University. We're very pleased about that with WSU as one of our partner teams. He received awards from both of those schools. He received the Graduate Alumni Achievement Award from WSU and the Purdue Outstanding Electrical and Computer Engineering Award from Purdue. He's also received several honorary doctorates, and you can look at in his bio for the places that he's done that. He's written dozens of technical papers in the area of digital relay design and reliability. He holds more than 100 patents worldwide pertaining to those topics. He received the 2012 Medal in Power Engineering. That's the highest award given by IEEE for leadership in revolutionizing the power of electrical power systems with computer-based protection and control systems. So all of those things are, I think, fantastic accomplishments and recognitions of what Ed has done to really change the field in electric system delivery. But we're also very thrilled that he and his company have been with us and help support us through this entire 11 years we've been working on this topic. So Ed, thank you very much for coming and spending time with us. We're very appreciative, and we look forward to your talk.
Well, good afternoon to you, and thank you for the introduction. The older I get, the longer that takes, and we really appreciate teaming up with TCIPG at the University of Illinois. And well, it's as you pointed out now, it's over a decade of us working together, and very much appreciate the opportunity to be here with you this afternoon. So I want to talk a little bit about the basics, a little bit about history, and sometimes that's going to help us figure out where to go. First thing I want you to think about is that how lucky we are to be part of an industry that delivers its commodity at the speed of light. Nobody else can say that. So over there on the left, we have a transmission line moving electric power at 186,000 miles a second. It's 11 inches a nanosecond, 6 microseconds per nautical mile. So in the middle, I got a railroad train of coal cars moving maybe 50 miles an hour, and over on the right, a pipeline. Looked long and hard until I could find a 3-phase pipeline.
We've learned about 3 from Pete.
Thanks, Pete, for laughing at the joke. It was generous. So the line pack in there probably moves about 30 miles an hour. So years ago, I was driving under the 345 kV line up by Old Skokie Boulevard in the Chicago area, and I realized here's a train pulling coal to a power plant. That's what we do for a living. We can take that the thermal energy in coal or oil or natural gas, convert it to electric power, the most versatile form of energy, and deliver it to people who want it at the flick of the switch. And the cool thing is, unlike the tank of gas in your car, you pay for it after you use it. So it's really an interesting thing. If that line over on the right is carrying 1,500 megawatts, then to supply that line from a coal plant would mean one of those cars full of 100,000 pounds of coal every 15 minutes. Now, the power plant is probably putting out more than that, but just for 150 megawatts, there might be 4 of those lines going out of a power plant. So just think that one line is moving a train car full of coal at the speed of light every 15 minutes. So I don't understand train cars very well, so I converted that into, it's 250 pounds of coal per second, something like 30 gallons of oil per second. Or you put it another way, in milliseconds, because second is a long time for stuff moving at the speed of light. So you about 1/4 of a pound of coal every millisecond. And again, we are able to get the energy to where you and I want it at the flick of the switch at the speed of light. And that's important to think about, as it sets us apart. I don't care how fast the drones fly. If Amazon ever figures that out, we're still going to beat them moving energy at the speed of light. In fact, our friends in the communication industry might think that they move energy at the speed of light, and they do, but we're still 50% faster, and I'll tell you why. They're moving energy at the speed of light in glass, and it goes downhill from there. So you think about the speed of light in a medium is equal to the speed of light in free space divided by the square root of the relative permittivity of the medium. Remember that? So when I taught electrical engineering, my boss, Harriet Regas, one day she told a bunch of us, I want 2 things out of the physics department, F equals ma, and you can't push on a rope. Well, there's a couple other things that was good to learn too, and I'm sure she would agree. So here are the information in a fiber goes about 200 or 2/3 because due to the fact that the light travels slower in glass than it does in free space. Plus, our circuit breakers don't slow down energy. It moves right through there at the speed of light. And compare that to switches and routers that have jitter buffers and so forth. Okay, so let's talk about staying safe in the information age. Let's talk a little bit, we can learn from history, do a little bit more on what makes power systems work. How can technology really contribute to it all? How do we stay safe in doing this, not getting into trouble, so that we really benefit from the technology, the strengths of the technologies? Most technology involves risk. So on the right, we see a poster from World War II that says, disaster, broadcast receivers can help the enemy sink you, don't use them. Now I have this poster hanging in a room to remind me of the importance of security. So I'm going to give a couple examples here. One of them is early Earth return field telephones in World War I, and another one is on this local oscillator radiation, and also something about false beacons. So somebody had the smart idea to set up field telephones using one conductor with an earth return. So the telephone, the communication tech would drive a stake in the ground, get on his horse with a reel of wire and spool it out to the next location, hop down, drive another stake in the ground and hook up the other telephone. So then they could have a conversation through the earth. They liked the single conductor because, well, if you used two, you could only go half as far for the amount of wire you were toting around the battlefield. So the problem with that is that the enemy can worm in on the communications, if you don't mind the pun. We thought it was kind of funny. I don't even get a chuckle. That slide just was wasted, I guess. So, because the field telephone of the good guys and the bad guys both shared the common conductor of the earth. So let's go back to that local oscillator problem of the shipping. So here's a partial block diagram of a super heterodyne receiver. And the whole idea is if you want to tune in to 1250 kilohertz, the local oscillator down there in red would be set to 1705 so that the difference would be 455 kilohertz, the frequency selected by the intermediate frequency filters and amplification of the radio set. Now the problem, that's the intended mode of operation. And I don't show anything for the detector or anything farther out over there on the after the IF amp. But the problem is the sneak path through that mixer going out back to the antenna. And some of the energy at 1705 kilohertz might escape, if you will, go up to the antenna and appear as a carrier at 1705 kilohertz of so-called local oscillator leakage. So this was known to happen, and the so-called morale receivers had this problem. So it's not really the reason I put the question mark on there is that this technological weakness that people feared was being exploited by the Germans was a real bad for morale if somebody's going to be able to send your ship to the bottom. So warning labels, this red warning label on that Crosley receiver says, warning, do not use aboard the ships, unsafe radiation limits. The sailors were taught, only turn these things on when you're in port. Here's another example. You know about beacons and as a navigation aid for shipping and aircraft. And here we have a airplane that's tracking in, homing in on a beacon. And the problem could be that if an enemy wanted to misdirect the airplane, they would set up a false beacon, a so-called meaconing, and pull the airplane off its intended course. Now, if the white thing was the Germans in World War II and the green things were the British, then the British did a very good job meaconing off German bombers, which dropped a lot of ordnance, fortunately, into the sea instead of in population centers. Another example of this might be the Berlin air corridors. If you recall history, that there were 3 corridors into West Berlin, into Tempelhof. And those corridors were 20 miles wide. So the airplane would fly in on a non-directional beacon at Tempelhof. And the fear was that the East Germans or the Russians would set up a false beacon to meaken the airplanes off course and then say they strayed out of the corridor and take them down. Okay, so here's some more basic thoughts. That power systems are inherently stable. So let that sink in for a minute. Here we are, we're talking about computers and communications, but we got to realize that power systems ran fine and run fine without computers and communications. So what it it's incumbent upon us to make sure when we apply computers and communications that we don't lose that basic fact in order to go after some perceived benefits. So, the question going forward then is really how do we take advantage of computers and communications to make power systems more efficient, to reduce outage times, to be more environmentally successful without giving up this inherent success that we have inherited from Edison and Insull and many other pioneers. So I get down to another point here is that protection has to be maintained at all times. And if we're going to take some protection out of service, at times that means we're going to take the primary equipment out of service. Another point here is that faults must be cleared fast. Finally, the green thing down there says communicate more, depend on it less. So as engineers and scientists, we should work on both sides of that. Instead of becoming totally dependent upon communications, how can we benefit from it and maybe even become less dependent upon computers and communications? Here's a 100-mile line between S and R. That's my end and your end. And let's put a fault right in the middle of that. And if we say it's 100 nautical miles, then the speed of light is 6 microseconds per nautical mile. So by the time you and I know anything about that fault right there in the middle, the fault is already 300 microseconds old, 50 times 6. So now let's suppose we're going to figure out whether to trip our circuit breakers because of that fault. That's the job of the protection. So I'm waiting for you to tell me if you saw it in the forward direction, in a directional comparison scheme, and you're waiting for me. So it's 300 microseconds by the time you know it, and if you could tell me through free space or on the transmission line itself, it would be the line length, 600 microseconds, so we're already into it 900 microseconds before I could possibly trip my circuit breaker based on my information and yours. Pretty interesting, huh? You can't beat it. If the fault's closer to me, it gets worse, because if it's right in front of me, then that's 600, and it's almost 600 plus 600, so it's about 1.2 milliseconds. And if we stick the signal into glass, as we're wont to do with a chunk of fiber, well, we're going to add on another 400 microseconds to it. Here's another point that we've had great success. Arc flash, unfortunately, kills somebody every day in this country. So you've probably heard about arc flash hazards. So here's a protective relay, 2 of them actually, that operate on current and light. In this oscillogram, you can see the fault current appearing in all 3 phases. And the middle trace there shows you the light flash intensity as a red trace that jumps up there in a hurry. So we use a combination of light and current, so we don't have to wait for any fuse to blow or any time coordination whatsoever, and this technology saves lives. What was security like when we did our first relay in 1984? First of all, we had 2 access levels. Now think back, 1984 meant 300 baud, maybe 1200 baud, but even 300 baud beat making a trip out to a substation even 30 miles away if you wanted to find out what happened. And we were very interested in delivering that capability to people because we could tell them where the faults are. One trip in a helicopter to patrol a line equaled the cost of one of these instruments at that time. That's how quick the payback is. So we said, if we're going to hook stuff up to a phone line, that was the way to do it then, we got to make sure that we put some security. So I said, we're going to do 2 levels of access control. So if you get right on the serial port on the back of this and you send carriage returns to it, you get a splat for a response. And if you put in the command access, ACC on the screen here, then it'll come back and prompt you for a password. And even then we used all printable ASCII characters. So case was important, and you could use anything on the keyboard and then some. So if you got it wrong, it would give you 2 more tries. If you got it wrong 3 times in a row, it would bang the alarm contact. So then you had an independent means of knowing if somebody was running passwords. So let's take a look at that. Here's the setup. There's your terminal on the left, a modem, a public switch telephone network, or maybe a private network of the utility, another modem in the substation, possibly some other switching stuff, and the digital relay. So as I mentioned, you do the access and the password, get it wrong 3 times, the alarm contact bangs. You connect that alarm contact up to the SCADA system, and now we've got authentication, or at least a notification of a problem, and the next slide will show the way we authenticate. So at that first access level, the only thing you can do is look at history and metering data. You cannot operate the breaker, you cannot set the relay. You cannot put software into it. That was it. So every time you put the second access command in, which depended on successful completion to that first access level, every time you even tried to get there, you'd bang the alarm contact again. Because now I thought you were doing something serious enough that the operator needs to know. We had customers tell us, would you disable that because we're irritating the operator? And we said, no, we will not. And we have not and won't. So then you put the password in. If it's right, you have access. And if you put it in wrong, then you want to try again, well, you'll bang the alarm contact again. And that was, a lot of security for 1984. So here's another way that even for some customers, they say, this is 1984, right? That they said, we want to be even more careful. So the difference in this picture is that switch to the left of the modem in the substation. Do you see it? So the idea is I call up the control center and say, hi, I'm Ed. I would like to talk to the relays in the Illini substation. So the operator would say, he might ask me, where did your mother grow up? And I'd say Danville, Illinois, which is true. And he'd say, okay, good to hear you, Ed. And how much time do you need? I say, I need a half hour. So he will then send a SCADA command to close the switch. A relay contact, so there was air between the phone line and the modem until the operator closed that contact via SCADA. Even then, he could see the normal state of affairs happen during the access process. So I think we did a pretty good job in '84, and that was before the internet, and that tended to speed things up, and things got a lot more serious. More on that in a minute. So in 2000, Dr. Oman and Dr. Frinke and I wrote a paper presented at the Western Protective Relay Conference, which I saw Dr. Frinke a couple of years ago at her new job, and she had that paper on the desk, and she said, Ed, people bring this in and they say that's one of the earliest papers they ever found about the topic of the day here. So in that paper, these are some of the things we pointed out back then. The pressure to downsize, automate, cut costs. Sounds similar to what was going on at banks. Instability in the electric utility job market. Remember FERC 888 and the restructuring, and there was a lot of involuntary layoffs brought out by that. And growth of computer literacy. Well, you could read the rest of these things. And a lot of increased access via modems and then the internet, and people concerned about security around the world. So here's what people wanted. They wanted connectivity, which equals convenience plus risk. So that's boo yay. Yay, we get convenience, and boo, there's risk involved with it. So in 2001, we put the first Ethernet port in our relays, and wow, it was fast and free, very convenient, unfortunately to bad guys as well as good. And a person in the intelligence community asked me one day, Ed, why would you ever put an Ethernet port on a protective relay? And there's my answer: market pressure. Now, it's a tremendous tool, but we have to use it right. And of course, that's what your organization and our company are all about. Now, I'm all about the kind of research that you do, that we do, and that we're doing together, because the best way to predict the future is to invent it. We even have that on the floor of our research and development building. So we're not going to get there by regulations. We're going to get there because of smart people like you and TCIPG, and smart people who work for electric power utilities and other manufacturers who understand that it's in the best interest of their companies, their customers, their shareholders, and the country to get this right. And meanwhile, regulations won't get there because they're going to come up short. By the time the regulations come out, the threat and the technology have moved on. One size fits all probably won't work. And they also tell the bad guys what we will do and won't do. Because so many people will think, well, if I'm compliant, that's good enough. And of course, compliance and security are different. The role of the government needs to be these two things only: to teach the threat with all due respect for sources and methods. And the second one is to advise on the best ways to secure communications and information systems. No more. Okay, so let's go on. Here's a SCADA setup that's being run through one of our distributed networks that we call ICON, for integrated communications over optical networks. And there's an SNMP connection to a computer in an operations center for the network. And that's all pretty good until somebody takes another blue cable there and connects the bridges, the corporate WAN to the control WAN. And now we're exposed to the control, or to the corporate WAN. I'm not even talking about the exposure that better not be happening from the corporate WAN to the internet. So one of the things you can do then is you fear that that threat could come in through the corporate WAN, go through the blue cable, end up in the network operations computer, and then do harm to the control network. So just like we put a switch, remember the relay contact controlled by SCADA? Well, if you do need that blue cable in between there, it's okay to put an Ethernet switch dedicated to the task of only permitting the communication and the bridging during such time that you and the operator mutually agree that that access is necessary. So this is part of a defense in depth for security, all the way from the relays to the aggregation in a substation up to the wide area networks, and be the access by serial or more modern technology. Again, we have to take a broad look at this. So who's familiar with Tempest? So there you go, about half of us here in the room. So the idea is that dotted box here would be the security perimeter, say, for a secure compartmented facility, like a military base or something. And you can see a teleprinter, because that's when this problem was discovered. And the teleprinter operator typed the word cat and it goes into a crypto box like a KW7 or something at the time, and the encrypted message comes out on the red side there as QMX or something. So the problem is people found out the hard way twice of unintentional radiation from the teleprinter. The teleprinters at the time had printer magnets in them and 60 milliamp DC control circuits wetted with a 125 volt battery to make them move fast. So these things they were screamers. So there were people that would set up antennas outside comm centers at certain remote places. Japan it's been declassified where they first caught it the second time actually. And somebody noticed a dipole when they were on a neighboring building. And somebody then started making measurements of the secure facility there and realized that the teleprinter itself was radiating. Then people got really interested and noticed it was also leaking out on the power line, and great strides were taken then to prevent it. We seldom talk about that when it comes to our own cybersecurity. So we have to look at all aspects of the problem. So the importance, we've brought some of the posters. One of the things that I started at least 10 years ago was, maybe not quite, 5-10 years ago, was making posters. So I remember the one I showed you about the local oscillator radiation from World War II. I said, let's start making modern versions of those. So here's a one on patrolling security parameters. Might as well have said perimeters because I almost did. And then the security in depth with the hamburger one. I think that hamburger one is one of the most popular ones. You can download these things for free from the selinc.com website. And we brought a number of them up here, and we're always coming out with new ones. And here's two more. They use strong passwords. I like the I don't share my toothbrush or my password because it's really kind of gross to think about sharing a toothbrush, but it's even worse to share a password, I think. We also started making some USB tags because of the physical and cyber vulnerability of USB ports. They're all over everything. And the vulnerability there can at least be warned, sort of like an ordnance tag on a weapon or a warning tag, say, on a pitot tube of an airplane. And these say USB devices may contain malware. So we ship every one of our products that has a USB port with these plugs in place. And we got a couple of bags of these, and take some, and you can get them free just by you do get online and say, I want some, and for some reason, they'll send you 90 at a time. I have a feeling that number was very scientifically determined by how many fit in a plastic bag. So here's another one, is the importance of physical and cyber security. So I hope that our talking about this a little bit helps us all step back, and we got to look at that whole hamburger and not just the meat. Here's a little security gateway thing that we make that senses motion. So if somebody's trying to pry open, this is a recloser control, a great place for it. If they're trying to pry it open, or if some car runs into the power pole, it'll set off the motion detector. The other one, and I'm talking about physical motion of the device as opposed to a security kind of motion detector, but it also detects light. Sort of opposite of the refrigerator. Here's where you let the light in, and an optical sensor notices that, and you get an alarm. In addition, there's a crypto and the cyber things that we're used to talking about inside that. Let's talk about this icon for a minute. Some years ago, we sat down and said, what is dependable communications for critical infrastructure? So we said it must be, security has to be designed in from the start, utility ratings, fast healing of 5 milliseconds, not per node, but 5 milliseconds over the wide area network. Deterministic. When I'm telling a protective relay, don't trip, I don't want to find out that the packet took a little longer to get there. than what we thought. Absolute microsecond network time. Happy to say we're down below 100 nanoseconds on it. And the best of TDM and Ethernet combined, the TDM being time division multiplex. Let's talk about that for a second. It's funny, the world started out with the frequency division multiplexing, went to time division multiplexing, and then to packet. So it occurred to me one day that TDM is set up so nobody talks to anybody until they get their time slot assigned to them. Packet stuff says everybody talks to everybody until there's a bunch of rules saying that he and she can't talk. Kind of interesting, huh? But in any case, this was a clean sheet design based on performance and security and quality, manufacturability, and price. So here's an example. The transport bandwidth for the TDM loops is about 2.5 gigabits a second. But what we can do is break that up into pipes, each pipe consisting of one or more time slices. So we gave some examples here. The top one there is a set of video cameras. So they get whatever we assign them, say a pipe this big. And if something happens, there's a lot of motion in a substation, well, it's the video bandwidth or data rates that the packet rates that go out are limited to the size of that pipe, so it can't step on the control teleprotection things of, say, 61850 or permissive transfer tripping. So we can control the bandwidth in Ethernet and other time division multiplex applications according to the task at hand. And again, we chose TDM. We had a choice. We could have used TDM, we could have used packet. So here's the explanation of a test we did later on to demonstrate the difference, because many people questioned us. And we said, well, this was an obvious choice. The TDM gave us a 600 microsecond net delay on a certain size network. MPLS, it was up at about 7,500 microseconds, and the jitter of MPLS was greater than our delay. So one of the fun things that you guys and we have been working on together is software-defined networking. So this is what is life like after not-so-rapid spanning trees. And the idea here is, of course, the network server tells the switches which way is a primary and a backup and secondary paths appropriate to the communications activities that we know are to be carried out. One of the advantages we have in these power system networks is we know the kinds of packets that helps us with, or messages, helps us with the whitelisting, and we also know who ought to be talking to whom. And both of those are big security advantages, and you and we have put that to work with the software-defined networks. Now, pilot needs to know where he is. Sometimes I'll ask the pilots, where are we? And just for them to have a little fun with me, they'll say, 45 minutes out. So, of course, what I meant is, where are we over? And of course, they know that too. Used to be they would do it by airspeed, barometric altimeters, compasses, celestial navigation, charts. In fact, this guy Jepson started a chart business to help airmail operations. It's now become a major business that airlines and all pilots depend on. Is now owned by Boeing. ADF, airborne directional receivers that observing non-directional beacons, VOR, DME, ILS, radar altimeters, and GPS. Now, once GPS happened, it seems like a lot of people forgot about the 5 bullets and the 10 topics on those 5 bullets above it. The other one is inertial nav systems. So there's really no excuse for not knowing where you are. GPS works great, and let's never forget we have other ways of knowing where we are. Us power engineers, we want to know what time it is to the microsecond, and frankly, I'd like to know what time it is to 10 nanoseconds for the traveling wave relay work that we're doing. So we've got an advantage that substations seldom move. There are mobile substations, but even then, once they're parked, they get wired in and stay put. And satellites we're doing about plus or minus 10 nanoseconds, 1 sigma today with our satellite clocks. Terrestrial networks, we're doing about 10 nanoseconds, 1 sigma. And then you couple that with disciplined standards, such as oven-controlled crystal oscillators, and we have very low drift rates. In fact, just for a second, let's think about 60 hertz sine waves again. That 1 electrical degree at 60 hertz is 46.29 something microseconds. So hey, we're not going to be off by a degree if we're down on the order of a few microseconds. So the holdover times of a decently designed oven-controlled crystal oscillator, like we put in our satellite clocks, keeps us there with way less than an electrical degree of error if we lost the satellites. Another one to look at is the VLF broadcasts, like WWVB at 60 kilohertz. It's a free source, and you just need a receiver to get it. And the inaccuracies of that have to do with, well, do you really know how far you are from WWVB, and do you really know the radio path? And we'll stay tuned and talk about that another time. GPS time is not guaranteed. Now, you read the articles just like we do, and you see a lot of people are making a big deal out of jamming and spoofing GPS as if that's a big surprise. But if you want to have some fun, Google Nav War. And look at that picture over on the green thing. That's a solar flare being observed in 2006 that took out GPS because of propagation for about 10 minutes. Could have equipment failure. You also have to remember DoD controls the U.S. satellite constellations for time. And, oh, by the way, I was flying over New Mexico not too long ago, over White Sands, and there was a notice to airmen of a big cone of, not silence, but a cone of where in the NOTAM they said where GPS is not going to be reliable. And our pilots told us that the airline pilots were really unhappy because they didn't want to have to go back and use the other tools we mentioned. So I'm not so sure why people think that jamming and spoofing GPS is such a new thing, because you go back to the days of radar. Radar really started full swing in World War II. In fact, our British friends invented the magnetrons, which are a vacuum tube that lives to this day in our microwave ovens. So the idea is that green radar antenna puts out megawatts, which attenuates as 1 over r squared, where r is the distance to that red airplane, paints the skin of the airplane, and some milliwatts come back. They drop off by 1 over r squared. So the round trip path from the radar back to it goes down by 1 over r to the 4th. So you don't get much back. So that's why it's real easy for a radar countermeasure set putting out just a few watts of noise to make a great big mess on the radar screen. So the idea then is there's countermeasures, and we've been through a lot of this over the years. So in our GPS clocks, we take advantage of our knowledge that these can be jammed and spoofed. So we look at the United States satellites and also Putin's satellites. So the blue ones are ours and the red ones are his, see? And they better agree on time. So that's one check that we can make, and if they're not, something is wrong, either with the receiver, the satellites, or somebody is up to no good. Meanwhile, remember, we also distribute precise time through the terrestrial networks, without any risk from GPS. We don't need it, but we use it if we have it. So another thing we do is we can take time. Let's suppose that the satellite clock gets it wrong and says, I think it's remember George Carlin, the hippy-dippy weatherman, where he said it was 10 o'clock in New York and 9 in Chicago and 8 in Denver and 6:42 in Los Angeles? So if the satellite clock is telling us it's 6:42, and we're really, really confident in the time, but the terrestrial network is saying, no, it's 7 o'clock, then this 3400, which distributes precise time, compares the two of them and says somebody's lying. Because if they're both giving you good quality time bits and the times don't agree, then there's something bogus. We can figure that out. So even in time integrity, now I'm bringing this up because we like it for power systems. I said, you remember, we're so concerned about phase angles across the power system because the phase angles determine the power flow. So I did that for Pete's benefit. He said, are you going to do the tie thing? So there you are. Here then, we also are interested in precision time in the telecommunications industry. If you go by cell sites and take a good look at their antennas, which is a lot of fun if you're a geek like me, but to look at those antennas, and you will see GPS antennas. So the first thing I would do if that was my cell site is I'd hide the antenna. I don't mean I'd bury it because it wouldn't work too good that way, but I'd make it look like something else. So, or else one way or another conceal its presence. Otherwise somebody's going to say, that's an obvious target. The other thing is the two constellation comparison, terrestrial failover, the authentication, and further quality checks in the instruments themselves and in the applications is still another layer below that. So I'm not the least worried about using precise time because I know that we have a number of steps to go through. And educating and teaching about this, something that you and we do individually and together, makes it a good thing to do. So wrapping up here, here's a few serious suggestions. One, never, in red, never connect SCADA to the internet. Number two, if you don't believe me, ask our VP of R&D. He was just here. He probably said the same thing when he was here, didn't he? Number two, operate private and secure control networks. If your process is critical infrastructure, you make sure your control network is treated as critical as any refinery process or any generation or transmission or distribution process. Consider time division multiplexing, not just packets, and the TDM does have those advantages of less delay and jitter. Apply defense in depth with layers of security, and I don't need to tell you guys at a university how important it is to learn and innovate and educate. And it's a good reminder that creativity happens not in a room, but between the two ears of an individual. It's something that stems from the self. And the education fertilizes the creativity that goes off in your mind or my mind or his or her minds. Let's encourage our government to teach the threat, again, with all due respect for sources and methods. Keep your security plans both private and compartmentalized. Understand the physics of the underlying processes. When I used to teach school, I'd advise the students that the poor students that got assigned to me as their advisor, and they'd say, what should I take? And I'd say, take stuff that don't rust. So electromagnetics and control theory, things that are going to be around a long time. So you could take some applied stuff for fun, but be sure you mainly take stuff that don't rust. So that's what the university's best at teaching anyway. So understand the physics of the underlying processes that you're trying to control and improve using computers and communications. Finally, to wrap up here, power systems run just fine without cyber. I may be kicking my own goal, because that's what we do for a living, is we make digital protective relays and digital SCADA systems and digital communication systems. But we have to give our due respect to Edison and Insull and the other pioneers before us who demonstrated clearly that power systems run fine without cyber. And the second bullet is where we all come in, is that computers, communications add to the safety, reliability, economy of the electric power. And I am sure with your work and ours and those of our others in our industry that we can build cyber safe solutions. Thank you very much.
My name is Prosper Panompabi. I'm a power research engineer. I work with RTDS to support 4 activities. I need to motivate my question before asking it.
Not too long.
Yeah. From the power grid of Tesla and Edison, the power grid is becoming more and more complex. And the power protection has to follow the power grid change and challenges. From basic protection, how we had in the past, now we envision adaptive protection. We are talking about settingless protection. And the mission of the university is to listen to the need of the society. I always felt that here at Illinois, we are missing something, is the course of the power system protection on undergraduate and graduate level. Such courses will be required to have a power system protection lab. A power system protection lab where a student and the researcher will be having opportunity to work with transmission relay, distribution relay, so and so. So my question to you as a president of a Blue Box company is I want to know how much you might be supportive of idea to assist us in acquiring a power protection lab at the ECE department. I know that at this time we have some postgraduates who are willing to compete if the course of protection system is an opportunity here. Thank you.
Okay, thank you for the question, Prosper. Gosh, you brought up a whole bunch of good things. One is you talked about increasing complexity. So one thing the digital protective relays did is they reset the complexity of the electromechanical world. Things got real complicated before we reset it with a digital technology in 1984. Now, one of the best compliments that we could ever get is when people say, you've got 2 of those, we want 3 or 4. You store 5 event reports, we want you to store a dozen. Now that you store a dozen, we'd like 50. We want faster sampling rates. We want, more and more and more. Then the complexity goes up. So I challenge our guys, who's going to be the next person to reset the complexity again? Is it going to be us or somebody else? And I'll tell you, it's going to be us. The one thing we're doing to reset the complexity of protection, you already mentioned it, the zero setting relay. We made the first zero setting relays for differential protection. And you wouldn't believe what a challenge that was. I used to walk around and talk to the designers and say, okay guys, how many settings does the zero setting relay have today? I baited them. And then pretty soon they got it that the answer was 0. So then there was a smart guy came to my office and he said, Ed, we got a setting. We can't call it a 0 setting relay. So what do you mean you got a setting? And he said, yeah, we got a setting for the address so that we don't have a communications loopback problems. You know the loopback problem where somebody loops the same fiber all the way back. And I said, that's an address. That's not a setting. And the guy argued with me some more, and I said, listen, when you sit down to write a letter, what do? Do you say you're addressing the letter or setting the letter? So that was the end of the argument. So the only thing that you can do is address the communication port. So we do have zero setting relays. And you know, customer near here is a very large user of those zero setting relays. The industry likes them a lot. And the third one you brought up was society, and that all led into working with your university and setting up courses and laboratories for teaching electric power. And we would love to be a part of that. And we have a formal, really, you write me a letter, and we take it from there to see if we can make that work. We also have 4 books today that could be used one way or another in power system protection courses. So thank you for the question. How'd I do? I answered okay? Thank you very much.
Thank you, Ed, for the great presentation. Obviously, over the years, you guys have been pushing the envelope in many different realms, PMU capability being built into your relays from day one, effectively. On the cyber front, you guys are building a lot of capabilities like that as well. But in the PMU space, you saw that while people bought your relays, they weren't necessarily using the PMU functionality for many, many years. Now PMUs are starting to uptick. Have you seen the same thing with cyber, and how are you guys addressing that in terms of building in these latest and greatest features? Are they being asked for by the utilities, or are you just building them in and saying, here's the features, please turn them on?
If you build it, they will come. The PMUs were a good idea. We embraced that technology early on, but I thought it was kind of silly to have to install another box, maybe $30,000 box, and wire it up with separate test switches, have separate software, and then someday have to integrate the data from that with the protective relay data anyway. It was silly. So we put that in there, and all of a sudden people realized that, wow, instead of a couple hundred PMUs, there was, 100,000 PMUs, and now perhaps 1 million PMUs, because every relay is a PMU. So something like that just became a standard capability that we've all come to appreciate. And all kinds of new applications come when you make technology readily available like that, essentially for free. One of the fun ones is that you go to commission a substation, every relay being a PMU, that if you hook them all up, say, to the same voltages, that all the voltages should look like this. All the phase A's better be pointing the same direction. If one of them's up here, you know that somebody rolled the phases. So people are now using the synchrophasers to reduce commissioning times and mistakes that lead to misoperations because of synchrophasers right inside the substation. So when it comes to security, we designed security, as you would agree, in from the day one. That we've been very careful about it, and we've kept up with that. So I think that's going to continue. That second example I gave, the one that showed the SCADA switch to open and close the phone line upon operator approval that it's you and not some fungo from Mars trying to get into the thing, that idea came from a customer in Minnesota, and we never sold anything to do that other than it tied so well in with our systems. So we're going to see a lot of collaboration and working together in the cyberspace as well as the electric power. Thank you.
So Ed, this is the last question, unless there's someone else who Burning. Oh, we have one who's burning. Okay, we're going to let someone else ask the last question. Students always come first.
My name is Vesta. I'm from Computer Science Department, and my question is that you talked about lots of physical security. You talked about prevention and all of that. How about if the attack happens, for any reason that your system has been under attack? Is there any functionality, logs, auditing, learning from that attack that it can, later on record it, replay it, and apply it to your design?
Yes. I didn't talk about much of our current practices in security, but our protective relays, our Ethernet switches, our computers, our ICON networks have what you would, as a computer guy, recognize as the security, the authentication, and the user logging. And yes, you have access to, of course, all of that information to use as you would in any other IT system. I do believe the way we've done it is a lot easier to use. That's what our customers tell us is, wow, this is sure easier than what our IT guys go through to get to the same point. So we're really into that, and we're happy to be partnering with you on it. Our guys like Dennis Gammo, Dave Whitehead, and Ryan Braithwaite and others are truly experts and pioneers in these areas. So thank you for the question.
Well, thank you very much, Ed. That was a wonderful presentation. I think a few people might come up and ask you more questions, but we need to sign off. From the broadcast point of view, we very much appreciate what you and your company has done to help us through the years. So let's all congratulate Dr. Schweitzer one more time.